Hello and good morning everyone. Today inshallah I will continue with you. This is our last lecture in eigenvalues and eigenvector, and I'm very happy that this is our last lecture in this for this semester with linear algebra. You will find, as I told you previously, I've sent all the PDFs to you on the WhatsApp, and also you have the recorded lectures and the revision lectures on YouTube. I will upload this lecture as soon as we finish it, inshallah. What I wanted to say is the second term, it's gonna be mainly starting from the part of vector spaces, the definitions of vector space, subvector space, how to check the relations, the intersection, the addition, the union of two vectors, sub-vector spaces, the kernel, the image for a linear transform, and also finding the eigenvalues and the eigenvectors and all the previous topics that we already talked after the first midterm. The second midterm is really very important. It needs your focus, it needs you to study very well in order to have good marks in this exam. And it is really very simple once you start working with it, and don't ever forget to use your pen while you are solving, reading the questions, and then reading the exercises, watch the video, then resolve these problems using your hand, and you have extra problems in the worksheets and everything. So you should be in a very good shape. Just only I need you to study good. Okay, I will do a simple recap between this lecture and the previous one. I believe by the end of the previous session, I spoke with you about the quadratic forms. And as I told you, quadratic forms are very special nonlinear maps that can be defined using matrices, and a very important rule in optimization theory. You will have this in Calculus 2 or Mass Analysis 2 within next semester. It's really very important in optimization. So, by a quadratic form, we mean this part from a polynomial, which contains the terms either to the power of 2 or terms multiplied in each other. So if I have like x1, x2, x3, and so on, I will have x1 squared, then I will have x1, a term containing a coefficient of x1 and x2, a term containing a coefficient of x1 and x3, and so on. Then I will start with x2 to the power of 2, also with terms like x2 times x1 coefficient, and so on. All of these coefficients can be gathered, and it will be used later in order to get this matrix, which is supposed to be in case of dealing with a quadratic form, it's supposed to be a symmetric matrix. So the main issue of writing the quadratic form and the corresponding matrix related to it is how to link them together. How to use this matrix in order to get your quadratic form, or vice versa. Then I will start dealing with this matrix, getting its eigenvalues, eigenvector, the orthonormalized model matrix that will help me out through diagonalization, because we already ended the previous lecture knowing that for a certain matrix I can get a similar matrix, link it to it, but on a diagonal form, which will make plenty of evaluations or calculations down the road, or any applications much easier. So, for example, for a quick example before we continue, if I have, for example, and this is the main part that I want to focus to be sure that you understand it very well. For example, if I have in a 2D, I'm talking about R2, let's say I will have the cube of an x and y such that is given by 3 of an x squared plus 6 of an xy plus 4 of an y squared plus blah blah blah. This is the quadratic part that we are dealing with. Of course, the remaining of this equation may contain or may not contain elements like 6 of x plus 4 of y plus 12 or something like this. So once we talk about the quadratic part, this is the part that I'm required to deal with. It's really very simple. I can put it on this form. I can put x and y for the row matrix times a square matrix, which is 2 by 2, and then a column matrix with the dimension 2 by 1. Of course, this is 1 by 2. If you can see the dimensions, it works beautifully. So if I want to get the elements of this matrix out of this system, it's really very simple. I will take the element 3 and the coefficient 6 and the coefficient 4. The arrangement will be like this. I will consider this is the first component, and that's the second component. So x squared stand for x1 element a11. So it's going to be 3 in the element 1, 1. And for y squared, it will be 2, 2. That means 4 will go for the position of 2 by 2. And for the element x times y, it will be 1 times 2. I will take the half of this number with its sign. So if this is positive, the value will be positive. If it is negative, the value will be negative. I will divide on 2, then I will have something like this. This is the corresponding matrix to this quadratic form. So if I did this multiplication, this is the quadratic part that I will have. Also, I can do it for a larger matrices. For example, if I have for a Q of an x, y, and z, for q, x, y, and z, which is such that will equal to, let's say, 2 of an x squared minus z squared plus 4y squared plus 2 of an xy minus 3 of an xz plus 4 of an yz plus blah blah blah, the other terms which consists of x, y, z, and the constant number. If I want to use this quadratic part in order to write a quadratic matrix, or the matrix corresponding to this quadratic form, it's also really very simple. All I have to do is exactly like what I did. I will see the axes or the components or the symbols that I'm dealing with, which is x, y, and z, as you can see. Okay? Just a second. Okay, let me change this pen. It seems like this pen is not working properly. So if I write x, y, and z, then I would have x, y, and z. And let's go. For the value of x squared, it stands for the element 1 and 1. So this is going to be 2. For y squared, as I told you, this is number 1, that's number 2, and that's number 3. So I will go for y squared, which is the element 2, 2, so it's going to be a 4. So I will go for 3, 3, which is z squared. The coefficient of z squared is negative 1. Remark, I'm moving with the numbers according to the arrangement of x, y, and z that I already wrote. Then I will have x and y. X and y is 2, so I will take half of it in x and y and the other half in y of x, which means 1, 2, and 2 and 1. Just only half and half. Then I will go for the xz coefficient, which is negative 3. In a similar manner, also I will divide it by 2, putting the half of it in the first row third column, so it's going to be negative 3 over 2, and the other half on the third row first column, which is going to be negative 3 over 2. Then I will go for the last value, which is 4y of z. I will divide it on 2, put half of it on the element second row third column, and vice versa. This is my matrix, or the matrix that I will be dealing with, as I told you. Let me get rid of this part first, because I'm afraid it's going to appear on the on the board. So just a second. Not too sure about this one. Yeah, it's working. Okay, very good. Okay, once more. In order to reserve this board, we will need it down the road, so just to clean it. So this one for you also. Yeah, voila, done. Here. So as I told you, that's the quadratic form and that's the corresponding matrix. So this is a symmetric matrix exactly like the ones in the beginning of our slides that we dealt with previously. The following couple of slides will contain plenty of information. So I will go through them with you and I need you to study them really very well. So if B is a basis for R of n, so it contains U1, U2, U3, a bunch of vectors, all of them, we say that B is orthonormal. When it's gonna be, this space is also normal. It will be orthonormal if the following conditions already satisfied. The first of them, the vectors U1 up to n are mutually orthogonal, which means if you take any two vectors of those vectors and multiply them in each other, the result will be 0. So as you can see, U1 times U2, U1 times U3, U3 times U4, all of them will equal to 0. Because we already that the inner product or the dot product for two perpendicular vectors, the sum of this inner product, the result will be 0. And we already have this by the first lecture or in the first lecture. For all I doesn't equal to j. So for any different two vectors belongs to an orthogonal basis, once you multiply them together in inner product, the result will be 0. Remark number 2, the two vectors u1 and u and up to un are unity vectors. Unit vectors, it's related that the magnitude of this vector is coming to 1 or is equal to 1. So once more, what's the magnitude of a vector? It's simply the sum, the square root of the sum of the squares of its components. So it will appear right, it will appear after a while. So now recall the dot product defined to Rn, just confirming the results. This is the dot product. So if I have U and V, and then I'm doing an inner product or dot product between them, I will have A1 times B1 plus A2 times B2, and so on. This is the dot product, it's gonna be a scalar thing. Okay, that's the norm that I told you about, or that's the magnitude of a vector, which is simply, it is the square root of the sum of squares of the elements of this vector. So it's gonna be the first component to the power of 2, second to the power of 2, and so on, and this is gonna be the magnitude. So any vector, I can get its magnitude, and if I divide each component on the magnitude of this vector, I will get a unit vector for sure, and this is how to get a unit vector out of any vector. All I have to do is to divide the components of this vector on the magnitude, and we already did that by the beginning of this part. Once we got the eigenvectors, if you remember, we get the magnitude, and we divided each component on the magnitude, and we have the final result. Okay, very good. Note that the dot product allows formal definition of lenses, norms, and the angles and orthogonality. This is one of the main issues. And once more, if u dot v is equal to 0, it means you have an orthogonal relation between these two vectors. This will play a key role in having the orthogonal matrices or the orthonormal matrices down the road, which will have a great property, as we said previously, which is its transpose is the inverse of this matrix. Okay, once more, let A be a real n by n squared symmetric matrix. Then all eigenvalues of A are real. All the values are going to be real. Then U1 and Un are eigenvectors of A associated to distinct eigenvalues, and then U1 and U2 are orthogonal, which means their multiplication will equal to 0, and we really checked that previously. Once we started solving a main problem, after getting the eigenvalues and then getting the corresponding eigenvectors, if you are dealing with a symmetric matrix, which came actually from a quadratic form, you will find these vectors orthogonal. Okay, number 3, there exists an orthogonal basis of Rn out of these eigenvectors. A is diagonalizable, so now I have a similar matrix for A. So if I have A, I can get a similar matrix to A, which is on a diagonal form. That's gonna be D equal to BT times A times B, where B is the normalized matrix out of the eigenvectors like what we did previously. Okay, B is the matrix whose columns vectors are the vectors of the orthogonal basis. Beautifully. B is said to be orthogonal matrix of V, and we already checked that. Okay, now I can do also a renaming or for the principal axes, if you like, to make a change of coordinates. And this is really very simple. All I have to do is to get the old components, old values. Like for example, I can say that for the XY main variables, okay, from which I got my symmetric matrix, after getting the diagonalized matrix or the relation or the normalized matrix, multiplying it by X capital, Y capital, okay, so this is X and Y capitals, and this is the A matrix that I got from the quadratic form. If I did this, or this multiplication, I'm sorry, this is the A star matrix, which is the also normalized matrix that we got from the eigenvectors, and we normalize it also. So if you get this relation, I can now connect the X and Y component to a new component, which is X and Y. And in this case, your quadratic form, the new quadratic form, but relative to those axes, it's gonna be lambda 1, the first eigenvalue, times X squared, lambda 2 times Y squared. This is gonna be the quadratic form that you updated quadratic form based on the change of variables that you did. This paragraph is trying to explain this property for you. Okay, now I have Q of X, and I will talk now about the definite or the definiteness of the quadratic forms. If it is positive definite, negative definite, semi-definite, and so on. Okay, we can say that a quadratic form, which is the part with x squared, x, y, and y squared, is a positive definite if for all values of x, the value of q of x is greater than 0. So if you are getting a quadratic form out, this quadratic form for all the values of x, or for all the domain, all the results will be greater than 0, then you will have a positive definite quadratic form. That's a huge, it has huge applications in maximizing or minimizing certain function down the road, not in this course, but in other courses or other applications. Positive semi-definite, it will happen if q of x, if the value of the quadratic form, okay, it has positive or equal values to 0 through the values of x which belongs to R. Of course, negative definite, it will have all definite values. Definite negative semi-definite, it may happen when you have some of the values are equal to negative values and others equal to 0. Once you have positive or negative values, you will have indefinite quadratic form, and that's the classification of the quadratic forms based on the definiteness of the or the signs of the quadratic forms, as you can see. Okay, note that QA is equal to X transpose times E times X, and it's positive definite, as I told you. Also, this definition can be given based on the inverse of the negative definite. But mainly, definitely, we will go with the first one. Also, this classification, I did go with you in the previous lectures based on the eigenvalues. So if I have an eigenvalue for the matrix corresponding to a quadratic form, I can classify it as positive definite, positive semi-definite, negative semi-definite, or indefinite. Really very simple. Once you have its eigenvalues and once you have its eigenvalues. So simply, if all the eigenvalues are positive, so it's going to be positive definite. If some of them are positive and zero, so you will get positive semi-definite. If all of them is negative, it's going to be negative semi-definite. It's going to be negative definite. If some of them are negative and for some values you have zero in these eigenvalues, then you will have negative semi-definite. If the eigenvalues, some of them are positive and others are negative, then in this case you will have an indefinite case for the indefinite case. So as you can see, we have 5 cases: positive definite for all values of lambda positive, positive semi-definite if greater than or equal to 0, negative definite if all of them are negative, negative semi-definite if they share 0, and then indefinite once you have some of the eigenvalues positive and the others are negative. Sometimes getting the eigenvalues of a matrix is a little bit difficult because actually you're stuck with solving an equation with 4th degree, 3rd degree, and this is not easy to deal with. Of course, the theory of equation will be applied in order to make your life easier in order to get the values of the eigenvalues, but still it's not that easy. So is there any other method that I can use? Yes. This is one of the simplest methods, which is the main principle or the main principles of a matrix, which is very, very simple. If you look to the matrices, if this is my matrix, let's say a 3 by 3 matrix, in order to give the idea, I can formulate, a bunch of matrices with smaller dimensions. I will start with this matrix on the principal element. It's written here, it's going to be on the n upper left submatrices of A. I will start with this matrix, which is A11, that's the dimension 1 on 1. Then I will increase the submatrix to be a 2 by 2, starting from the left. So it's going to be A11, A12, A13, A12, A22. So then I can deal with the whole matrix. If I have 4 by 4, then this is going to be a submatrix. Then I will have a full matrix. So now I have A1, A2, and the A3, this is the whole matrix as you can see. And you can spread with the dimensions if they are bigger than that. According to the determinant, the determinants of these submatrices, I can define the quadratic form relative to this matrix by positive or negative definite and so on. Okay, the first definition states that the quadratic form Q of x, xt ax depends on A. It's a positive definite. If and only if all the upper left submatrices determinants are positive. So I can, if A1, this element, the determinant of this matrix is 1, is positive. The determinant of a 2 by 2 matrix sharing the same principal diagonal is also positive. And the determinant of the whole matrix is also positive, then I will have positive definite. Okay, if I went to have negative definite, it will happen, but with a special arrangement of the values of the determinant of these matrices. It will happen if the matrices with odd order is negative values and the others are positive values. If this happens, it's going to be negative definite. Otherwise, it's going to be indefinite. So, once more, I will get the determinant of A1 if it is less than 0. The determinant of A2, it's an even determinant, so it's an even number of this determinant. So it's going to be if it is greater than 0. And then for A3, it's going to be negative. A4, if it exists, it's going to be positive. In this case, I will have negative definite. If this condition didn't apply, I will have indefinite type of this quadratic form, and that's what's stated in here, as you can see. Okay, that's another way in order to a classification for your quadratic form. Okay, graphs of quadratic forms in general. So for q of x equal to ax squared, and this is for the case of positive definite, as you can see. For all the values of x, the value of q of x equal to x squared, it is positive values. If you multiply the coefficient or change the coefficient, you will find this matrix, it's closing its wings like 2 over x squared. So simply the 100, it's going to be q of x, 2x squared, it is the one in green, as you can see. And that's a quadratic or positive definite quadratic form. That's a negative definite, as you can see. For all values of x, the value of the quadratic form is negative. And once more, this is for x squared, and that's for negative 2 over x squared. So it's a negative definite. For the elliptic paraboloids, or I'm sorry, for the 2-dimension, if I have x and y, so the previous ones were for 1 dimension, but if I'm dealing with 2-dimension, like an x and y, if I have x squared plus y squared, which is a positive definite, of course you will have an open bound to the up, and it will give you a minimum point. And this is why I told you it's really very important in maximizing and minimizing down the road or in optimization. So that's a positive definite quadratic form. The other one, it's a negative definite, as you can see. I believe the graphs here are just for you to understand how it's going to be a positive definite, how is the shape, negative definite, how it's going to be the shape, and the applications will be down the road, as you can see. Also, I can have the positive semi-definite. So for stuff like positive semi-definite, how it's going to appear? It's going to appear like this. This means some of the eigenvalues are positive and others are equal to 0. So you will have just only x squared in 2 dimension. Or like this one, y squared in 2 dimension, and that's a positive semi-definite. For this couple of curves, it represents the semi-definite, the negative semi-definite, which represent one of the axes, one of the eigenvalues is 0 and the other is negative. And as you can see, it's looking down, it's looking downward, and it represents a parabolic cylinder, as you can see. Also, we can have, if I have some lambdas positive and others are negative, which means the quadratic form for some values of x will be positive, for other values will be negative, and in such case, you may have the hyperbolic paraboloid or the saddle bores. The names here are just for you to be familiar with the shapes, but they are not involved in your exams. What's really matter is how to classify a positive definite, definite, positive definite, positive semi-definite, negative semi-definite, or indefinite. But the shapes is just complete the idea. Reaching to that point, this is the end of our course. We already finished now. And I will need to go with you just for a couple of problems once more on eigenvalues and eigenvectors, or to finish the worksheet at this time. I will solve a problem with you, and also there is we started already solving from the previous session. You will have the problems with the beginning of the sheet solved over there. But this is a very interesting statement or problem. He wants you to show us that let A belongs to an n by n matrices, so A is a square matrix. Show that A and the A transpose share that same characteristic polynomial, and therefore they will have the same eigenvalues. If they have the same characteristic polynomial, or the polynomial that you will get your eigenvalues from, which means they will have the same values. So how to prove this? It's very, very simple. I will start from reading this question. So I will need to write the characteristic polynomial. So I will start, if A belongs to the n by n matrices, then the characteristic polynomial will be a minus lambda times I. That's the equation that I will depend on in finding the values of the eigenvalues. That's what we do. Okay, and also knowing that since A is equal to A transpose as determinants, and this is from the property of determinants, now I can write the characteristic polynomial of A transpose, which is going to be very, very simple to prove that for a characteristic polynomial of A transpose minus lambda I, it's exactly like getting the determinant of an A minus lambda I transpose, and according to this property, now I know that it is exactly like A minus lambda I determinant, which means the solution for this guy is exactly like the solution of this equation, and the eigenvalues will be the same. So this completes our idea. Therefore, A and A2 have the same characteristic polynomial, and so they have the same eigenvalues. It is proved. Also, I had it earlier on this slide. So the characteristic polynomial, as you can see, it's the determinant of A minus lambda I. Then the characteristic for A transpose is determinant of A transpose minus lambda I. So, and I want you to remember that this reality, it's from the properties of determinant. So, of course, this is going to be true, which leads to that the determinant of this matrix is equal to the determinant of A minus lambda I, which is equal to the determinant of A minus lambda I, which means the characteristic polynomial for both the matrix or its transpose, they are exactly the same. Okay, this is one of the standard problems. He wants you to solve this problem in order to get the eigenvalue and the eigenvector. So he needs you to compute the eigenvalues of A, provide an orthonormal basis, this is the B matrix, composed by the eigenvectors of A, determine the orthogonality in the diagonalized matrix, where B is a diagonal matrix, explicit the quadratic form QA defined by A, is it positive, definite, quadratic form, and so on. Of course, all of this will be dealt with, especially for the classification, if it is of the definiteness, if it is positive definite, negative definite, or something, once you evaluate your eigenvalues. So all I have to do now is once more get back to that characteristic polynomial, and I will try to solve. So this is my characteristic polynomial, A minus lambda I equal to 0. So I will take the elements on the principal diagonal, subtracting the negative lambda from each element of them, and then expanding this determinant, which is going to be lambda squared minus 4. This is lambda squared minus 4. Then I will try to factorize it, which is going to be a difference between two squares, leaving you with lambdas equal to negative 2 and lambdas equal to 2. So now I have the eigenvalues, which are negative 2 and the positive 2. I have the eigenvalues. Keep them with you. I will now go to get the eigenvectors. So now, for lambda is equal to 2, I will go to get u2. And this is really very simple. All I have to do is to solve the system, which is A minus lambda I times u equal to 0. Either u1 or u2. So I'm getting u1, this is the first vector. So it's very, very simple. All I have to do, as I told you, is to solve the system, which is 0 minus 2 for the eigenvalue, 2, 2, then 0 minus 2, and that's a homogeneous system, as you remember. And which will lead to that I will have negative 2 and 2, then 0, then I will have 2, negative 2 and 0. The second step will be negative 1, positive 1 and 0, then all the elements are zeros. Now I can expand this equation as the following. This is u1 first component, u1 second component, which is equal to 0. So I will have u1 sub 1 equal to u1 sub 2. That's the relation connecting these the two components of the vector, as we did previously. So the first eigenvector u1 will consist of first component, second component, then I will replace the first component by u12. So it's gonna be u1 sub 2, u1 sub 2, substitute, so you will have u1 is equal to 1 and 1, and that's for the first eigenvector. That's the first eigenvector. In a similar manner, exactly in a similar manner, I will redo this matrix, but with lambdas equal to -2 in order to get the other vector. And once you do so, I believe it's going to be a -1 and a +1. This is for u2. If you remark, these two vectors are orthogonal, because -1 times 1 is -1 plus 1 times 1 is equal to 1. Now I can get the matrix B. The matrix B is really very simple. Okay? So the matrix B is gonna be, I will put the first vector, which is 1 and 1, the second vector, which is -1 and 1. I will divide the first vector on the square root of its component, similarly like for the second one. Then I will have 1 over root 2, 1 over root 2, then -1 over root 2, 1 over root 2. That's an orthonormalized matrix, where its inverse is its transpose. So this matrix will have this property, and from which I can get the diagonalization. As I told you, that's the first step, trying to solve the system. We got y is equal to -x, since we are dealing with lambda 1 is equal to -2. So that's the eigenspace, which is 1, -1. So that's the first, as we are dealing with u1 is equal to, the first eigenvalue is equal to -2. Once you're dealing with lambda is equal to 2, that's the eigenvector relative to it. I have the two vectors, already checking if they are multiplied, they are orthogonal. Okay, so I can get an orthogonal matrix out of this. Okay, now I have the magnitude of each one of them, which is come up to beautifully to